Welcome to the third module of the NI Multisim Basics course. By the end of this module, you should be familiar with a few of the many analyses offered in Multisim, how to enter expressions for the computation of analysis, and how to effectively use the grapher and the information it can provide. Let's start by taking a look at how analyses work in Multisim. Many different types of analysis are provided for examining circuit behavior, such as transient, noise, and Fourier analysis. These analyses require a circuit to already be captured and ready for simulation to run. Custom expressions can be added to your analysis to better visualize specific aspects of the circuit and the results of the analysis. The graph review is an interactive tool that helps visualize and measure results from conducted analysis. Using analysis is a four-step process. Assuming you have a ready-to-simulate circuit, we must first select the analysis that we wish to conduct and proceed to configure it by entering expressions, selecting output variables, and configuring the analysis and parameter options. Then, simulating the circuit, and finally the performance evaluation using the graph review and the post-processing options. Let's start by taking a look at the alternating current, or the AC, analysis. Remember, all the Multisim files used in the modules can be found in the attachment section. This example is the same one we built in the previous module, with a load that has been added to facilitate a power analysis on our circuit. We're going to conduct an AC analysis to understand the frequency domain behavior of our circuit and calculate the power at the output of our filter. Select the AC Analysis in the Analysis tab from the Simulate drop-down menu. Under the Frequency Parameters tab, you can define the range of frequency, the number of points, and the scale the simulation will be performed over. Under the Output tab, you can see the sections for the variables available to choose from on the left and those that will be used for analysis on the right, as well as advanced expressions and model parameter options. We can select parameters from the variables in the circuit panel, such as the current and voltage for various components in your circuit, and add them to our section for analysis. We can remove any variables, if there are any, from the Selected Variables panel, and add desired parameters for computation. In our case, we want the voltage at the output of our filter. From the expression options, we could add a mathematical equation for power dampening calculated from the variables in our circuit for analysis instead of just the variables. Multisim can save you a great deal of time and headaches in case you need to calculate expressions using the gathered data. We're going to test this out with a simple power calculation. Under More Options, we can add a Devices or Models parameter. We'll select our load resistor and choose the parameter to be resistance. This should add the parameter to our previous list on the panel to the left. Now let's add the expression P equals V squared over R. You can double-click on the variable name to add it to the expression. Accepting the changes and verifying that the output variables are correct, we can move on to the next section by clicking Simulate. This will open up the grapher. The graph review is not only for the visual display of the results from analysis, but every time a simulation is run, it saves the data gathered and displayed from the various instruments, such as the Bode plotter or the oscilloscope data. It can be used for precise cursor measurements as well as the management of the data through saving, printing, and exporting to programs like Excel. You can compare more than one result with overlay functionality and create annotations and even place data labels. In the graph review, clicking on the Show Hide Cursor button on the toolbar will create a pop-up window displaying the information from the cursor on the graph. This will display useful information such as the position of the line, coordinates, and gradients. Right-clicking the cursor will give us a few options for cursor movement. If we go to the next Y max, we can see the cursor reposition itself on the highest value of the y-axis found in the graph to the right of our current position. We can close the grapher window, but the data will still be retained. Rerunning the analysis, but removing the power equation from our output panel will yield just the voltage dependent on the frequency. We have two graphs, the magnitude and phase graph. To successfully work with a graph, you need to have it active by clicking on the left side of the one you want to work with. In our case, we want to work with the magnitude graph, so we click on it and notice a selector pointing appearing. Right-clicking on the left axis and selecting Axis Properties will allow us to edit the view of our graph. Because we selected left axis properties, it took us directly to that tab. We'll properly label it with gain in a decibel scale and range it from -50 to 10 decibels. We'll create 4 ticks with 2 minor ticks and a precision of 0. Under the Scale section, under the bottom Axis tab, we can change it to logarithmic ranging from 1,000 to 1,000,000. Once we click OK, the graph will change to our desired values. The same can be done for the phase graph by activating it, going into its properties, labeling it properly, and selecting a linear scale from -180 to 180 with 4 major and 1 minor tick, as well as a precision of 2, and applying the same bottom scale as previously used. Now, running the simulation once again to generate a Bode plotter and oscilloscope graph, we can stop the simulation and open the grapher again. It can be found under the View drop-down menu. Selecting the Bode plotter tab and the gain graph, we can overlay traces by going to the graph menu. Selecting our AC analysis from before, we can see how both these trace graphs are practically the same. The only difference being found near the peak due to the difference in sampling rate between the analysis and the instrument. This can be changed when setting up the analysis. In this example, we have the number of points increased to 100 from the 10 that we had in our previous analysis options. Once that is simulated, and you go through the same steps to procure the overlay traces, you will notice that there is no difference from our Bode plotter results and our analysis results. Next, we'll see how the output from our transient analysis holds up compared to the oscilloscope. Selecting transient analysis from our analysis drop-downs, set the simulation time from 0 to 1 milliseconds with a max time step of 1e to the -5. And allow the SPI simulation engine to estimate the time step based on the netlist convergence. Next, let's select the input and output voltage as our parameters to be displayed. If we were to simulate without selecting these, Multisim would redirect us to the section that needs checking. You can see the similarities between this graph and the output from the oscilloscope. The third analysis we're going to cover in this module is the Fourier analysis. With the Fourier analysis, you can learn about the different frequency components of any signal. Let's prepare the same circuit that we had for a Fourier analysis. After selecting the Fourier analysis, we can just ask Multisim to estimate the best analysis parameters for us. Of course, you can manually configure both the sampling and the transient analysis options for the Fourier transform calculation. Select the input and output voltages as the variables to be depicted and simulated. Notice the results are presented with both a graph and a chart, and 2 tabs are created, one for each variable selected. Finally, our last analysis we'll prepare the circuit for is a Monte Carlo analysis. Monte Carlo analysis helps predicting the performance of the circuit under non-ideal conditions of some circuit parameters, such as a component value. Add a tolerance to show the capacitance from capacitor C1 with a tolerance type of 20% in a Gaussian distribution. Then after accepting and repeating the step above for C2, we can set the analysis to run an AC analysis with 5 runs and showing the output. We can configure this analysis by editing it to have a frequency from 1 kHz to 1 MHz and with a decade sweep of 100 points and a vertical decibel scale. As you can see, the Monte Carlo analysis helps you learn how the variation of this capacitance values shift the bandwidth of this filter design. We will learn how to use the post-processor to manipulate the results from the analysis. But first, a quiz. Welcome to the fourth module of the NI Multisim Basics course.